about work done by non-constant forces. So we know that, like we've said a bunch of times, work is equal to the integral. This is a one-dimensional case, x initial to x final of f dot d. I'll make this a little dx. That's our dr, that's the displacement, except that's a little displacement in the x direction, okay? So this is equal to the integral from x initial to x final of f dx cosine of theta, where theta is the angle between the force and the displacement. So if it's on the x-axis, I mean, it's pretty simple. Here's 0. This is the x-axis. Okay, let's say we have some force like this. Here's the angle theta. And I'll just draw dx down here. You know, dx is in this direction, or dx is in the opposite direction, or something like that. The way I've drawn it, the angle between f and dx is over here, could be back here. So if f is along the x-axis, okay, like we've had, you know, in the past where you have just a force that's a simple force along the x-axis, then theta, we can take care of that. It's just x initial, x final of f dx, where this f, depending on the SIGN of f, that gives us the direction. That takes care of this cosine of theta. But for a non-constant force, x initial to x final, f may be a function of x times dx. Okay? So f can be a function, you know, f could be a function of time. It could be a function, the way I've written it here, you know, we're making it pretty simple where it's a simple function of x. Then we have to actually do this integral. We can't just pull f out front and look at delta x as far as that displacement vector. So I want to look at an example based on that. And the example is that of a spring. So for a simple spring, here's my simple spring, okay? Let's let this equal x. Let me just let it equal 0 for now, okay? So here's some 0 point, and here's some little loop at the end of the spring. That didn't line up very well. If you displace this spring, and here's the little loop, by some distance x, then that spring has a force. I realize there's some external agent that's having to displace the spring, but if you displace it this distance x, there's some spring force that is in that direction, okay? Now this spring that we're going to cook up also has the same ability in the other direction. Let's say you compress the spring. I'll draw it up here. So you compress the spring, and here's the little point on the end, okay? Then there is some force in this direction, okay? So you compress the spring, you get a force in that direction. You stretch the spring, there's a spring force in that direction. So the spring force, the model that we're going to use, the spring force is equal to minus kx. Okay? Does that work? Well, if x is positive, if this is 0, and you've stretched the spring, you get a negative, right? If x is negative, you're compressing the spring, then you get a positive spring force. And this is called the spring constant. Okay? That has to do with the material properties of the spring itself. You know, what's it made of? How stiff is it? How many little coils does it have? And this is measured typically in newtons per meter. So it's some force per unit distance. Okay? This is called Hooke's law. Hooke's law. And it's a pretty good model for simple springs that aren't stretched too far. Okay? So they obey Hooke's law as long as you don't stretch them way out where you're starting to bend the spring and deform the spring and so forth. So this is pretty good approximation. Okay? This is a vector. It's 1D. That negative, like I just mentioned, gives us the direction of the spring force. And by knowing whether x is positive or negative, we can figure out the direction based on that, whether the spring is compressed or the spring is stretched. Okay? So let's look at the work done by the spring. Any questions on this? This is a simple... Okay. So I'll rewrite the spring force is equal to minus kx. Okay. We're assuming that the equilibrium point, that means where the spring just sort of comes to rest, the equilibrium point is at 0. We can fix this up where you don't have to have the equilibrium at 0, but makes it simpler, okay? So the work done by the spring, I'll call that Ws, is equal to the integral from x initial to x final of Fs dot, well, forget the dot. We're going to take care of that because Fs is going to be negative. We've already taken care of the dot product. So this is equal to the integral from x initial to x final of minus kx dx. K is a constant. It depends on the spring. I can pull that out front, and this is equal to negative k times the integral from x initial to x final of x dx. What's the integral of x? Everybody knows that one. That's x squared over 2, so this is equal to minus k times x squared over 2 evaluated from x initial to x final. Okay, so this, in the end, I'll rewrite it up here somewhere. I'll write it down here. The work done by the spring is equal to 1/2 k x initial squared minus x final squared. That's it.
Dr. Clark,
Yes, ma'am.
did you have to let us all into this meeting? Like, click on the computer to let us in? Or did we just join? Because Juan is trying to get in right now.
Okay. I think I put the password over okay, yeah, I see them. They should be able to enter that password. But thank you for letting me know. So they're, okay, I apologize for that. They're here now. Okay. Hey, that looks pretty decent. Kind of sideways. Okay, so this is the work done by the spring. There is some external agent that is doing work to move this. The spring doesn't do this on its own, okay? Well, it has to be brought to some point initially by some external agent. So in moving this spring, the work done by the spring is equal to, let me say the negative of the work done by the spring is equal to the work done by some external agent. A hand moving the spring back and forth, you know, a bug pushing it along or something, pulling it along, something like that. Okay? So let's look at an example. Are there questions on this? Let's look at an example of what you can do with this. Okay. So I'll rewrite this up here. Work done by the spring is 1/2 K x initial squared minus x final squared. Okay. Here's a spring mass system. I wish we had more time. We could spend, weeks and weeks and weeks talking about spring mass systems. Here's a mass. Let's say it starts out here at 0. And it gets displaced down here by some external agent to x equals 0, so about 50 centimeters. Okay? So it gets displaced in this direction by 50 centimeters. I don't know what did it. Somebody pulled it down here. Okay? So how much work was done by the spring? Well, let's say a typical spring constant like we would use in the lab is about 30 newtons per meter. All right? So about 30 newtons per meter. So let's look at the work done by the spring on the mass. Well, we just plug it in up here. It's 1/2. Let me put K in there. It's 1/2 times 30 newtons per meter times x initial is 0, x final is 0.5, and you get a negative, so that's a negative 0.25 meters squared. Okay. So that's what, 15, and 1/4 of 15 is 3.75. Is that right?
Yes.
Negative 3.75 joules. Why negative? Why is this negative?
Not compressing it.
Yeah, well, if you compressed it, you would still have a negative amount of work done by the spring, right? Because then I mean, x final squared, so x final, although it's negative, you square it, you still get a positive. Yeah, what I'm after is all along this motion, the spring force was this way, was it not? The spring force was in that direction. So you had a force by the spring on the mass in that direction and a displacement in this direction that gave you a negative amount of work being done by the spring. Okay? Someone else trying to get in? Probably not. Okay. There was a negative 3.75 joules done. Okay. Let's look at the opposite case. Let's say that, forget about, what brought this mass to this point, and now somebody releases it. What's going to happen? This is frictionless. So this mass is going to be pulled by the spring force in this direction. So now once it's released, that spring is doing a positive amount of work on the mass. Let's say that the mass is 200 grams. That's reasonable. Okay. Can we calculate the velocity after this mass is released? Calculate the velocity at equilibrium, at the 0 point. Well, work is equal to delta Ke. Okay. Doesn't matter what's doing the work. The spring, the air, a person. If we look at the net work, I guess I should write net. The net work done, okay, then that's equal to the change in kinetic energy. The only thing doing work on this system, I'm talking about now, we release it. The only thing doing work on the system is the spring. So, I'll write it up here. The work done by the spring, the net work, is equal to 1/2 30 Newton meters. This is going to be a simple calculation. Now, x initial is 0.5 and x final is 0. So you get, instead of the negative, you get a positive 0.5. I'm sorry. This should have been 0.25. Okay, the way I wrote it before. All right. So this is equal to 3.75 joules. That's the work done by the spring, and that equals, we got a bunch of equals going on here. The change in kinetic energy, I'm going to get rid of this picture. I hate to get rid of it. I want to say something else about it. Okay. So delta Ke is equal to Ke and Ke final, that's what we're looking for. 1/2 mv final squared minus Ke initial, but that's 0. So we get 3.75 joules is equal to 1/2 0.20 kilograms times v squared. So we can calculate the velocity of the mass at 0 pretty easily now. So you get 37.5 meters squared per second squared. Okay. And all of that underneath the radical. And that equals 6 point something meters per second.
6.12.
6.12 meters per second. Okay. A gift from Zoom. What is this? Okay. I think I did that calculation right. The idea I want you to get is that now when we look at this second case, we release the mass, the spring's doing a positive amount of work. It started out at 0.5, it ends at 0. That gives you a positive number here. And you relate that to delta KE, and you can calculate the velocity. What would happen if some external agent moves the spring from, or moves the mass from 0.5 to negative 0.5? How much work is done by the spring on the mass, moving from 0.5 to negative 0.5? 0. Right? 0. Okay. You okay with that? In moving from 0.5 to 0, that's a positive amount of work. The spring force is in the direction of displacement, but moving from 0 to negative 0.5, that's a negative amount of work, and they cancel out, and you get 0 for the amount of work done by the spring. Okay? This is what happens in harmonic oscillators, simple harmonic motion. The spring gets out here to the point where the energy that was initially given to the system, that work done by the spring equals that initial amount of energy. It releases it, it goes back over here, and it stops again where that energy that was given to the system equals the work done by the spring and going over here. And you get this oscillation back and forth and back and forth. Okay? The change in kinetic energy from here to here is 0. The change in kinetic energy. All right. Lots and lots, innumerable things in nature are modeled with this mass spring system. It's a simple harmonic oscillator. Very simple system, but extremely useful. Okay. This is the work that you need to equate to the motion in this system. Any questions on this? Okay. I want to talk about conservative systems and non-conservative systems. Okay. All right. Here's a mountain peak. Here's an object. Okay. You move this object from ground level up here to some height h. All right? If you're in a conservative system, so conservative systems are ones where there are no losses. In other words, you don't have forces like friction, air resistance, all these things where the energy that you're having to provide to move objects around you're not having to work against those forces. Okay? Lots of ways to say it. I mean, I don't know if I have the official way written down or something like that, but so it really, let me say this though, conservative systems is path independent. Okay. It's path independent. Meaning, it doesn't matter whether I take this path to get up there, or I go along this way, okay? Doesn't matter what path I take. It only matters on where I started and where I end up. I'm storing potential, if this is a Earth, gravitational mass system, Earth mass system, then it doesn't really matter which path I take. The energy that I use to get the object up to this point is simply mgh. Okay, and that energy is stored in the system. Just like in the mass spring system that we looked at, that is a conservative system. There's no losses. Okay, I do some work on the system. That energy is stored in that spring. The spring can release that energy. Okay, it has the ability to do work. You can think about this. Let me show you on a plot. All right. If, let's say this is the y direction, this is x, just like always, and there's some force like gravity in this direction. And you want to start out here at the origin, and you want to get over here to some point xy. Okay? X, Y. All right. Well, if your displacement is like this, say this is delta R, okay? Then if you think about sort of the calculus or geometric idea, you have this dot product between F and delta R, and the only thing that counts is that portion of the force that's along this direction. So if you take that dot product, then you're going to get F dot delta R. It'll depend on the angle between the two. If you take this path, okay, you went along the x direction, but look, this force is perpendicular to x. There was no work done in that direction, and then you went up, and you get the exact same amount of work being done by this path as you would this path. Okay? There are no losses. There's nothing taking away energy from the system. Okay? Let's look at a non-conservative system. Ooh, I didn't want to erase my little drawing, but it's all right. You'll get a feel for this in a second. Maybe. Non-conservative. Path dependent. Okay. Think about the forces acting on an object. Let's say you have to push this object up a mountain. You take this path, you're working against friction for a long, long distance, okay? Not only did you have to put in enough energy to raise it to MGH, that's again, there's no way around that. You also had to work against friction to get up there. And you took this long, circuitous path to get to that point. Maybe someone on the other side, well, no, I said this was here, okay. However, maybe this is very, very smooth and this is a much shorter path. You reached this height in this same point, but you didn't do as much work against friction. Okay, it was a little shorter path. And then maybe someone else simply had the object at this point and raised it to here with absolutely no friction whatsoever. Okay? The energy that you had to put into getting this object to height h was different for all these three paths. That's a non-conservative system. Okay? You have losses. All real systems are non-conservative. Okay, all, not all. You could talk about superconductors and all these exotic kind of things, but in everyday life, all real systems are non-conservative. You always have losses. You always have some energy that you've got to put in that you don't get back, okay? So, in terms of work and kinetic energy, we look at the work done by conservative forces plus the work done by non-conservative forces, and that equals the change in kinetic energy, okay? So maybe you have an applied force, all right? This is some work done on the system. Or maybe this is gravity. This work done by these non-conservative forces is always negative. It's always slowing down the system for these non-conservative systems, okay? So let's think about like an object that we're always talking about sliding along some, or being pushed along some floor by some applied force, okay? This would be a conservative force, or it's an applied force, and Fk is this non-conservative amount of, what am I trying to say? Fk makes up the work done by these non-conservative forces, okay? So you have, through some distance delta r, like always, you would have Fa delta r, then you have minus Fk delta r. What happens to that work that friction did? Well, it goes into heat. It's thermal energy. That energy is, we think of it as being lost to the system. I mean, you rub your hands together, your hands get warm, okay? So this force of friction created some thermal energy, all right? So the work done by the non-conservative force, which is friction, is minus Fk delta r, and this is I'll just call it heat. Okay. This is turned into heat. It's lost to the system. It does not increase the kinetic energy of the system. It decreases it. Okay. What else do I want to say about this? So, if you look at, I'm going to do an example of this in a second with gravity. Okay. If you look at a system like a gravitational system or the mass mass spring system, we know that negative delta PE is equal to delta KE. That's that change, the negative of the change in potential energy. So this is PE initial minus PE final. Let me write it like that. PE initial minus PE final. Okay, that's delta KE. All right. Then if the initial kinetic energy, if your initial potential energy is greater than the final potential energy, okay, then you're speeding up the system. You're increasing its kinetic energy. That's like an object falling. If PE initial is less than PE final, what?
Okay.
I'm glad you're there. Okay. If PE initial is less than PE final, that's like raising the object. Okay. Something had to do some work. Gravity did a negative amount of work. It slowed it down. Okay. But then you have to add in this work done by non-conservative forces. It goes over here on the left side, and it's always negative. So the work done by non-conservative forces is equal to delta PE plus delta KE. So you look at the change in potential energy plus the change in kinetic energy, and that gives you the work done by non-conservative forces. In a conservative system, these two things are equal, right? I mean, well, let me put it this way. The negative, they're equal, like the negative of the change in potential energy is the change in kinetic energy. So they sum up to zero in a conservative system. I wish we had time to do all these demos and things. I have a great bowling ball demo that I do where you're swinging a bowling ball and you're in that conservative gravitational field and you're exchanging potential energy, kinetic, potential, kinetic, potential, kinetic. It's an interchange between potential energy and kinetic energy. However, there's always some friction and it's slowing everything down. Okay? So I want to look at an example based on this idea. Let us say that you go to a water park. I'm going to make it pretty simple. Okay? You go to a water park and they have one of those big, huge water slides. Okay. So what is a typical height for one of these water slides? Are they 1,000 feet in the air? Are they 50 meters? Are they 100 meters? Let's make a really big one. 100 meters. That is way, way up there. That's 300 feet. Okay, that's enormous. I don't know, somebody could look it up, world's tallest, highest water slide or something. Okay. So here comes someone, they're gonna go down the slide. Okay. They're not gonna jump, they're gonna slide. And here they are at the end. They're coming out of the water slide. And what is usually waiting down here? Well, you got water. I need blue. You got water all the way along here. There's usually a little, there's some kind of transition here. And then there's this big tank where you slow down, you hit the water and you slow down, okay, in some distance. All right. What's happening here? Well, if you were to fall from this height, okay, in a conservative system where there are no losses, when you reach this point, it's pretty darn easy to calculate your final velocity. It doesn't, remember, it's independent of the path, so it doesn't matter if you wiggled down or whatever you did. If there are no losses, then your final velocity, if you remember, so here, for no losses, okay, V is equal to the square root of 2GH, right? That's just equating MGH with 1/2 mv squared. Okay? So what would the velocity be? Well, this would be no losses, so you get 2 times 9.8 meters per second squared times 100 meters. That's about 22,000. What is that? What do you get? 14. Can somebody calculate this, please? 13, 14.
I got 44.27 meters per second.
44. Okay, I'm doing something way wrong. It's 20.
Is it 9.8 times 100
Yeah.
times 2, right?
Yep.
And then you just
It's 20 times 100.
So it'd be
2,000.
980 times 2, which is 1960, and the square root of that is 44.
Okay. All right. 40. What'd you get? 44 point what?
27.
27 meters per second. Okay. That's really fast. It's very, very fast. Okay. All right. You're falling from 100 meters. You end up exiting. This is no losses. It's a Teflon. You're in a Teflon suit on a Teflon slide. Okay. So you get ejected down here at 44.27 meters per second. But what's happening in the real system? In the real system, there is water all along the way, and usually some sort of big water stop down here that's taking away energy from the system. Okay? So let's say that in this case, that there is a force, let's see, I'm going to let this be frictionless, and let's let the stopping force, let's say that this person is about 80 kilograms. Okay. So, let's see. There's a lot of ways you can think about it. Let's say this distance from here all the way down to here. Let's say before they reach this little stopping area. Okay. Here they are. Okay. So that's 100 meters. Let's say this is about, I don't know. This is about 100 cosine of 45, which is, let's say this is 140 meters. And then this distance is another 200 meters. Okay. All right. So 140 meters, another 200 meters here. And we find out that they actually come out with a V final of 5 meters per second. Something fairly slow. Okay, so here's the scenario. They're an 80 kilogram person. They're sliding. Its total distance that they slide is 140 meters plus 200 meters. Okay. From that, we can calculate the losses. Let's see. Let's calculate the work done by friction. So the work done by these non-conservative forces is equal to delta PE plus delta KE. Okay? So they started out from rest. They started out with an initial velocity of 0 and at height 100 meters. So PE initial is equal to 80 kilograms times 9.8 meters per second squared times 100 meters. PE final is equal to 0. KE initial, 0. KE final is equal to 1/2 M, which is 80 kilograms, times 5 meters per second squared. Okay? So I want to know what is the work done by this water, this interaction between the water and the person along this path. Okay, so we get 89.8. That's 8. What does this work out to be? PE initial is equal to what? Somebody calculate PE initial?
78,400.
78,400 joules. Okay. KE final. That one's 25.
1,000.
It's 1,000. Okay. 1,000 joules. So the work done by these non-conservative forces is equal to, wait a second, PE initial, this should be negative. Because we're looking at, shouldn't be negative, but delta PE is PE final minus PE initial. So you get a negative 78,400 joules plus, because it's KE final minus KE initial, and that is plus 1,000 joules So the work done by the non-conservative forces is 400 joules. Negative. Okay. Okay, now, since we know the distance that this person traveled, we can calculate the average force. Obviously, the force that is, well, I don't know, maybe it's different, maybe the water levels are a little different, but obviously the force on the person by the water, the slide, everything else, that force is going to be in this direction, right? It's slowing them down. Their displacement is this way. So we can calculate the average force on this person. And I'll do that up here. So the average force is this work done by the non-conservative forces is negative 400 joules. And so that's negative 400 joules is equal to the average force times 340 meters. That's the distance traveled. So if I'm calling this the positive direction, F average will be negative. That makes sense. I guess, we could just ask for the magnitude. So F average is equal to negative 400 joules divided by 340 meters. And that is equal to what? 340, 10, 20 something? I don't know.
227.65.
227?
Yeah, 227.65.
228 newtons. Okay. All right. Had there been no force, okay, that person would have come out at, like we said, 44 meters per second or something. And delta PE would be the negative of delta KE. And that would sum to 0, but that's not what happened. They came out at a much lower velocity, so there were some losses. And the average force is 228 newtons. There are a couple of problems in the homework. Good morning. Are there any questions on anything? I'm going to tell you what's going to be on the test. And then if you have questions on homework and stuff, that's fine.
I have a couple questions for chapter 9 homework.
Okay.
And I have some questions for chapter 8.
Good. Okay. All right. So let's do the homework questions. Okay. Let's start with chapter 8. Which one's in chapter 8?
I had a question on 4B.
4B.
And then Burkett, did you have one on chapter 8 too? Was it number 5?
Yeah. Hold on, let me check.
Okay.
What?
It was 5C and 6.
Okay. So let's see, 4B is the spring problem with air resistance, right?
Yes.
Oh,
It's
okay.
the one that, like, the first one there was no air resistance, and then now there's an air resistance force on the object.
Yeah, okay. So when you've got the spring by itself, then you have the work done by the spring plus the work done by gravity is equal to 0. Okay? Because it's starting and then coming to rest, I think, right? Starts from an object.
It's compressing,
Yeah, okay. Yeah,
and then it's asking,
right.
yeah, the
Okay.
same thing, but just there's air resistance this time.
Yeah. So in this case, in part B, you have to add in the work done by the air resistance. This is part B. Plus the work done by the spring, plus the work done by gravity, and all of that is equal to 0 is the way I did it. This is non-conservative. It's a long word to write. Non-conservative, and the work done by air resistance is equal to negative FAY plus H. Okay. So then I got something like this. I got negative FAY minus FAH plus MGH plus MGY is equal to minus 1/2 KY squared is equal to 0. Then you can solve this for y, I think. Because you get 1/2 k y squared plus FA minus MG y plus FA minus MG H is equal to 0. So you get something quadratic in y. And I called H the height from which the object fell. Okay, so my picture, I mean, you can set it up a couple of different ways, but my picture is like this. So you have the spring starts out, and this distance, this mass is up here. It's about to fall. And this is H. And then in the next, after it impacts the spring, it's here, and this, and it has the mass on it. And this little distance is y. Okay? So in that, you have something quadratic in y, and you solve that. Then for part C, it's just a repeat of part A, except that Now G is equal to 1.6. That's easy. You got part A, right? Brooke?
Yeah, I did.
Okay. Okay. The reason, well, this is good. That should do it. Okay, so someone else had a question on 5. Okay.
5C.
5C, okay. At what height should the parachute be opened so that the final speed of the skydiver when he hits the ground is 5 meters per second? Okay. So an 84 kilogram skydiver jumps out of a balloon at an altitude of 1,320 meters and opens the parachute at an altitude of 185 meters, assuming that the total retarding force on the diver is constant 55 newtons, parachute closed. So you got a 3,600 Newton force with the parachute open. Okay, so let's see, at what height should the parachute be opened so that the final speed of the skydiver when he hits the ground is 5 meters per second? Okay, so in this case, he's 84 kilograms and 3,600 newtons. That's my version. Let me see. Is this chapter 8? Okay, I got the spring. All right. Okay. So here he is up at 1,360 meters, whatever it is, right? Then somewhere, I'll call this H. Somewhere he opens the parachute and starts to descend. And you want the final velocity in my problem to be 5 meters per second right here. Okay? So the force after he opens the parachute, what is the force? 55 newtons with the parachute closed. Seems like I had, let me see something. Let me see it there. Oh, maybe I had this. Yeah, here we go. Okay. I had it on the wrong. Anyway, so, let me change this a little bit to, okay. So this height I'll call H, and this height I'll call Y. So this is where the chute opens. Okay. So you have the work done by gravity plus the work done by the retarding force is equal to KE final. Okay. So the work done by gravity is the same throughout the whole thing. The work done by gravity is mgh. Now this is a different story. In this case, it is, oh my goodness. Sorry about that. Okay, in this case, WR is equal to minus RC. Oops, that's not right. Well, it's right, but I just put the, okay. Minus RC, that's the retarding force with the chute open, times H minus Y, plus or minus R0Y. That's, what did I call that? H minus Y. Oh, that's this. Oh, that's closed. That's open. I don't even know my own notation. Okay. So the work done by the retarding force in this section is negative the retarding force with the chute closed, and that distance is H minus Y. Then you have with the chute open, and that is this distance Y. So now in this case, for KE final, this is 1/2 m times 5 meters per second squared. Okay? So that's KE final, whatever your mass is and whatever your velocity is. So now you just solve for, the only unknown is Y. Because you have MGH, you know H, you know these, and you solve for Y. Does that make sense?
Yeah, I believe those.
Okay. All right, so that was number 5. Which one in number 9, chapter 9? If you watch the homework help on 9, you should be okay. Maybe I need to rewatch it. Which one's in 9? None of them?
7.
7. Okay.
From 7.
Yeah, I got you. Is that the one with the projectile hitting the wooden block? No.
No.
Nope. Okay. Oh, okay. This is the. All right. Okay, so a rod of length 26.50 centimeters has linear density, that's mass per length, given by lambda is equal to 50.0 plus 24x, where x is the distance from one end and lambda is measured in grams per meter. Okay. What is its mass? Well, if you have a linear density, lambda, then that's mass per unit length. So here's the x-axis, and here's the stick. Okay. So what you're doing is you're breaking it up into little bits of dm. So that is dm. So that's a little tiny bit of mass. And dm is equal to lambda dx. Because this is the mass per unit length, and that's a little bitty bit of length. Okay? So the mass, the total mass is, you sum all that up. So big M, I'll call it, is equal to the integral from 0 to, call this distance L, from 0 to L of lambda dx. Okay, well, I should have written just the integral of dm, but in this case, so that's the total mass. That's part A. For part B, how far from the x equals 0 is its center of mass? Well, center of mass is this x center of mass is equal to 1 over the total mass times the integral of x dm. Okay? It's 1 over the total mass times the integral of x dm. So dm is equal to lambda dx. So this is equal to 1 over big M, which you just calculated, times the integral. This will be from 0 to L of lambda x dx. Okay? I think that's right. Because it's the position times the little bit of mass. So you're going to have to integrate. Mine is 50 plus 24x. So lambda equals 50 plus 24x. Okay. And you can multiply that by x. And you get 50x plus 24x squared. You integrate that, evaluate it from 0 to L, and that's good.
You also go over number 5.
Yep. Number 5, okay. Let me see. I think I have that one. Chapter 9. Okay. Yeah. All right. All right, a 7-gram bullet, when fired from a gun into a 1-kilogram block of wood held in a vise, penetrates the block to a depth of 9.6 centimeters. The block of wood is next placed on a frictionless horizontal surface, and a second 7-gram bullet is fired from the gun into the block. To what depth will the bullet penetrate the block in this case? So this is a conservation of linear momentum and impulse problem. All right, so let's look at case 1. This is where the bullet penetrates, the block is stationary, it's being held, and it goes to some depth, okay? So here's the block, I'm just going to make it like stationary against a wall. And here comes our little bullet. That's a big bullet. And here's V initial and the mass of the bullet. This has some big mass M, which we really don't care about right now. And it goes into the block, and I'll call this D1. So that's the depth that it goes with the block stationary. All right? So from work energy, you get 1/2 mv initial squared is equal to F D1. I'm not going to go through all the work as delta K and all that stuff. Think about it. That's the energy of the bullet. That's how much work you had to do to stop it. F times D1. Okay? Now, in the second case, so that's the first bit of information. In the second part, here's big M. Here comes the projectile at some V initial, same initial velocity. Okay? Same mass, big M. Now, sometime later, it impacts the wood, penetrates the wood, and here it goes to some depth, D2, and now this object weighs little m plus big M. Okay, and this thing's inside there. Okay? So it goes to some depth, D2, and you get a V final based on that. So what happened in this case? This energy that was in this projectile coming into the block, part of that energy went into the bullet penetrating the wood, and part of it went into this thing moving on. But momentum is always, energy is not conserved in this case, all right? When we talk about kinetic energy and potential energy and so forth, what happens? There are losses when this thing comes to rest in the block. There's heat, there's sound, there's I don't know what all kinds of things there are. But momentum is always conserved in all cases, forever and ever, okay? So we can say that M V initial, that's the momentum of this by itself, the projectile by itself, is equal to little m plus big M V final. That's conservation of linear momentum. This is the initial momentum. This was at rest. This is the final momentum. Okay? But we also know that 1/2, okay, this is just for, let's see, what else do I know here? The kinetic energy is 1/2 m V initial squared minus 1/2 little m plus big M V final squared is equal to F, whatever that force is. I'm assuming these two forces are the same, D2. Okay? The work done on the losses, okay, where this, I'm lumping them into F times D2 here. This bullet penetrating, there were losses, there was some work done. That's where the loss was. It went into heat, it went into whatever, okay? So I've got this equation, I've got this equation, and I've got this equation. Let's see what we can do. I'm going to have to erase some of this stuff. So from previous, I'll move some things around. V final is equal to, I think that's little m. Yeah. Little m over little m plus big M times V initial. That's, yeah. So V final squared is equal to little m over little m plus big M squared V initial squared. Okay. Now you can make some substitutions, substitute that into that previous equation that you had FD2, and you get 1/2. I know this is on the homework help from the YouTube video, but that's okay. 1/2 mv initial squared times 1 minus little m over little m plus big M is equal to f d2. Okay. You make a substitution. But 1/2 little m v initial squared is equal to f d1. So you get f d1 times 1 minus little m over little m plus big M times f d2. We're assuming that that force, that average force in both cases was the same. So you get a what did I do? I left out. That's a really silly. Okay. Equals F D2. Okay. So now you get a relationship between D1 and D2, and I've got it written down. I'll just write it like this. D2 is equal to big M over little m plus big M times D1. And that's it. That's not obvious. That's a difficult problem. I think it's a nice problem to show you this interplay between momentum and energy and losses and non-conservative forces and all that stuff, but the algebra is a little bit tedious. Any other questions on the homework problems? Okay, so let's talk about the test. I know it's just unreal the way time flies. I don't know. Especially doing this remote thing, it's not optimal, let's say that. I feel for you. So what are we going to do? So for the test, I'm really going to attempt to make it very straightforward, because I know you have not had time to absorb all of this stuff. But anyway, number 1, so this is test 3. Number 1, work. You know, a box on a Flat surface, some forces are acting on it. What's the work done by different forces? What's the network? What's the change in kinetic energy? That kind of thing. All right. Number 2. Potential energy problem of some kind. Maybe a spring. Maybe like the one in the homework. Spring plus gravity. Maybe. Or maybe only gravity. I don't know. Okay. Some such problem like that. Number 3. Non-conservative forces. So I want to see if you kind of understand this relationship between losses, work done by non-conservative forces. So it'll still be a work kinetic energy. I mean, that rules everything. Work is equal to the change in kinetic energy, and it'll be some non-conservative force in there. So maybe like the slide with the kid on the slide or something like that. Okay. Number 4, I'll give you an impulse problem. An object impacts something. What's the impulse? Or it's hit by a tennis racket. It comes in at a particular momentum. It's hit by the racket, goes off at a different momentum. What's the impulse? What's the average force? This kind of thing. Number 5, very straightforward collision problem, not like the one we just did. Okay? So if you watch the videos, you know there are elastic collisions, inelastic, sometimes called perfectly inelastic. That's where 2 objects stick together. Perfectly elastic, where there are absolutely no losses in kinetic energy, this kind of thing. And then the bonus will be something from test 2. Okay.